Guys, this is my sign for your launch. No, that's alright. Guys, alright. I'm back. Now we can start in 5, 4, 3, 2, 1. All engine running. All engine running. 42 degrees miles per hour. 42 degrees miles per hour. This is just we're about to get in low Earth orbit.
Of course, you have tuned in once again in order to try and learn from my greatness, which I will display for you. Your attempt to try and improve yourself in the game is honorable, and if you watch my Unicom gameplay, perhaps you will eventually become just almost an inkling as good as I am. I will do it in the first two games of this. No Primavera and no consoles. No Primavera consoles, unlike some British CCs, which will
Stop
play the
second
overpack.
stage bro.
Can James Webb find planets around Centauri? Interstellar travel is horrible. What with the cramped quarters of your spaceship and only a thin hull separating you from deathly cold and killer cosmic rays. Much safer to stay here on Earth with our gloriously habitable biosphere, protected magnetic field, and near endless energy from the sun. But what if we could have the best of all worlds? No pun intended. What if we could turn our entire solar system into a spaceship and drive the sun itself around the galaxy? Well, I don't know if we definitely can, but I don't know if we definitely can't.
Okay, we got.
Moving the sun would be a prodigious technological feat, an act befitting a type 2 civilization on the Carter scale. The same technological realm as building a star encompassing a Dyson sphere. Although it'll be several centuries at least before we can reach that level, The actual physics of a stellar engine is easily explained in a short YouTube video in 2023, and that's what I'm going to do today. It's really just Newton's laws of motion. Newton's first law tells us that objects tend to coast at a constant speed unless acted on by an external force, say the mutual gravity of the rest of the galaxy holding our sun in its orbit. But it's also possible for an object to change its speed through propulsion, ejecting a smaller part of itself at very high speed in the opposite direction to your desired direction of motion. Newton's second law says that every action has an equal and opposite reaction. If, say, a rocket blasts its propellant, the act of blasting pushes the rocket forward. And this is just conservation of momentum. A stellar engine follows the exact same principle, with the one additional technical challenge of building a solar system scale structure to do the job. Although it sounds impossible to move something as massive as the sun, which weighs more than 300,000 Earths, we have a ready-made energy source to do so, the sun itself. It was Fritz Zwicky who first came up with a scheme to move the sun. Zwicky had a lot of wild ideas. He was the first to ponder the possibility of dark matter and predicted the existence of neutron stars and gravitational waves long before they were discovered. In 1961, he proposed the first stellar engine. It was a giant particle accelerator in space that shot pellets of the sun at close to the speed of light. With enough gravity, these would not collision on impact and blast jets of matter off at high speed, pushing the sun. The sun's material would be its own propellant and energy source, although we need to come up with at least enough energy to power the particle accelerator. Now, Zwicky never did the math on how much fuel this would take and how fast the sun could go, and in his classic style, he never returned to the idea. But the proposal inspired humanity, or at least a few of us, to start thinking about how to move the sun. Although the next serious proposal was well over 2 decades later. In the late 80s, Soviet aerospace engineer Leonid Shkapov came up with a concept that doesn't require any external energy source or even a propellant. The Shkapov thruster relies on the fact that light itself carries momentum. Each of those photons coming from the sun carries momentum away, and so pushes the sun an infinitesimal amount in the opposite direction. The push is very tiny, and photons are emitted evenly in all directions, so the sun really stays put. But what if the sun could be coasting, just shining a little more in one direction? Shkarov's proposal was to build a giant parabolic mirror made out of a super thin foil the size of a planet's orbit. Photons hitting the mirror would be reflected back, transferring momentum to the mirror in the process. If placed just right, this outward radiation pressure would be perfectly countered by the inward pull of the sun's gravitational field, enabling the mirror to remain in a fixed position relative to the sun. The mirror is a solar sail in the truest sense, powered by sunlight and pulling the sun itself. There are 2 ways to think about how this works. One is that we consider the sun and the mirror as a single system which radiates light preferentially in one direction. Conservation of momentum then demands the system accelerate in the opposite direction. Another way to think about this is of the mirror as a giant gravitational tugboat. In this interpretation, the sun's radiation does indeed cause the mirror to accelerate in the opposite direction
There's
of the
the
internal
another
photons,
mission.
but the sail's own gravitational field tugs the sun slightly so that our